Hi everyone, this is Ms. Shea. In this video, we will be looking at ionic bonding and structure. After watching this video, you will be able to define the term ionic bond, describe the formation of ionic bonds, deduce the formula and name of an ionic compound from its component ions, including polyatomic ions, and explain the physical properties of ionic compounds, including volatility, electrical conductivity, and solubility in terms of their structure. We will start by looking at what a chemical bond is. A chemical bond is a force that holds two atoms together and enables the formation of compounds. Atoms bond to achieve noble gas electron configuration. Noble gases have complete valence shells, so atoms achieve complete valence shells by bonding. Bonding only involves the valence electrons, or the electrons in the outermost shell. The core electrons are not involved in chemical bonding. To understand ionic bonding, we need to first review how ions are formed. Cations are positive ions that form when metal atoms lose valence electrons. Anions are negative ions that form when nonmetal atoms gain valence electrons. The number of electrons that are gained or lost depends on the electron configuration of the atom. Remember that the atoms are trying to achieve noble gas electron configurations, and gaining or losing electrons is the method for achieving that complete valence shell. An ionic bond is defined as an electrostatic attraction between oppositely charged ions. It is the result of a transfer of one or more electrons from a metal atom to a nonmetal atom. The metal atom becomes a cation, and the nonmetal atom becomes an anion. Both atoms achieve complete valence shells as a result of the transfer. The positive metal ion is attracted to the negative nonmetal ion. That attraction is the ionic bond, and the resulting compound is an ionic compound. One way of telling whether an ionic bond may form between two atoms is by finding the difference in their electronegativities. We say that if the electronegativity difference is 1.8 or greater, then an ionic bond occurs. However, the best method to determine whether an ionic bond occurs is to simply remember that an ionic bond occurs between a metal and a nonmetal. The location of an element on the periodic table can tell us what its ion's charge will be. The periodic table shown here gives the ionic charges of the elements. Group 1 ions have a +1 charge. Group 2 ions have a +2 charge. And ions of group 13 elements generally have a +3 charge. Group 15 ions have a -3 charge. Group 16 ions have a -2 charge, and group 17 ions have a -1 charge. A polyatomic ion is a group of covalently bonded atoms with a single charge, behaving as a single entity. The polyatomic ions that the IB requires you to know are ammonium, NH4+, hydroxide, OH-, nitrate, NO3-, hydrogen carbonate, HCO3-, carbonate, CO3-2-, sulfate, SO4-2-, and sulfite, SO3-2-. You also have an extended list of polyatomic ions that was given to you at the beginning of the school year. When we write the chemical formula for an ionic compound, the cation is always written before the anion. The charge of an ionic compound is always neutral, meaning that the positive charge of the metal cation and the negative charge of the nonmetal anion cancel out with each other. The subscripts in the formula of an ionic compound gives the ratio of the ions needed to make the charges cancel out. Let's do a few examples. Our first example is sodium sulfide. In this case, sodium Na+ is the cation and sulfide S2- is the anion. 2 sodium ions are needed to cancel out the -2 charge of the sulfide ion, so the formula is Na2S. In example number 2, we have calcium oxide. Calcium Ca2+ is the cation, and oxide O2- is the anion. The +2 charge of calcium cancels out the -2 charge of the oxide ion, so the formula is CaO. Example number 3, strontium hydroxide. Strontium Sr2+ is the cation, and hydroxide OH- is the anion. 2 hydroxide ions are needed to cancel out the +2 charge of the strontium ion, so the formula is SrOH2. Notice that the parentheses around OH and the 2 outside of it denote that there are 2 hydroxide ions for every 1 strontium ion. Finally, example number 4, chromium 3 sulfate. Chromium 3 Cr3+ is the cation, and sulfate SO4 2- is the anion. Notice the Roman numeral 3 in chromium 3 means that it has a +3 charge. In this case, we will need 2 chromium 3 ions and 3 sulfate ions to cancel out the charges. So the formula is Cr2SO4 Again, the parentheses around SO4 and the 3 outside of it denote that there are 3 sulfate ions for every 2 chromium 3 ions. Ionic compounds are formed as a result of ionic bonding. Ionic compounds are crystalline and have a 3-dimensional repeating pattern of positive and negative ions, which is called a lattice structure. For example, this picture shows the structure of a sodium chloride crystal. The purple circles represent the sodium ions, and the green circles represent the chloride ions. Notice the repeating pattern throughout the entire crystal. That is the lattice structure of sodium chloride. Here we see a photo of salt, or sodium chloride, crystals under the microscope. The lattice structure of the ions are reflected in the cubic crystals. Because the attraction between oppositely charged ions is very strong, the lattice structure of ionic compounds is very stable. This means that ionic compounds are solids at room temperature, have high melting points and boiling points, and also have low volatility, meaning that ionic compounds do not vaporize easily. The lattice structure of ionic compounds also affect other properties, such as electrical conductivity. In the solid state, ionic compounds do not conduct electricity. This is because the ions are locked in fixed positions in the lattice and cannot move. However, in the molten state, or the aqueous state, the ions dissociate and are free to move, and therefore ionic compounds can conduct electricity when molten or aqueous. Ionic compounds can dissolve in polar solvents, such as water. A classic example of this would be table salt dissolving in water. This is because the polar solvent molecules have partial charges. These partial charges are attracted to the ions in the lattice structure of the ionic compound. The individual ions get pulled out of the lattice and become surrounded by the solvent molecules. And as a result, the ionic compound dissolves into the solvent. However, ionic compounds cannot dissolve in nonpolar solvents, such as hexane. The nonpolar solvent molecules do not have partial charges. This means there is no attraction between the nonpolar solvent molecules and the ions in the ionic lattice. Therefore, the ions remain in the lattice structure, and the ionic compound does not dissolve.